Welcome children. As we are aware of what is principle of mathematical induction, we can now use it to verify some of the mathematical statements. Now starting with the first one, you can see it is sum of n terms which needs to be proved equal to n into n plus 3 over 4 times n plus 1 into n plus 2. If you look at each term, it is of the form 1 divided by product of 3 consecutive natural numbers. Now let us first verify it for n is equal to 1. That means for the smallest natural number. Okay, when we replace n by 1 in the left hand side, it reduces to 1 over 1 into 2 into 3, that is 1 over 6. In the same manner, we check it for the right hand side by replacing n by 1 over here. Again, you will find it reduces to 1 by 6, which is same as the left hand side. So this shows that our statement for which we use the notation Pn is true for n is equal to 1. So for the very first natural number, it is true as per the principle. Now the next thing we are assuming there is a natural number k for which our statement is true. Now under this assumption, we are going to prove the statement is true for the very next natural number, which is k plus 1. So when we assume it is true for n is equal to k, that means some of these terms where you can see n is replaced by k in the last term, the sum of these terms should reduce to k into k plus 3 over 4 times k plus 1 into k plus 2. Now using this, we will be proving the result for n is equal to k plus 1. So for n is equal to k plus 1, now we are going to prove 1 over 1 into 2 into 3 plus 1 over 2 into 3 into 4 and so on. The last term will be now 1 over k plus 1. See, this n gets replaced by k plus 1. So this reduces to k plus 1 plus 1, that is k plus 2. This will become k plus 1 plus 2, that becomes k plus 3. So we need to prove the sum of these will be equal to this much. Again, this is obtained by replacing n by k plus 1. So the right hand side reduces to this when we replace n by k plus 1. So this needs to be proved. In order to prove this, we are going to use our assumption, which is equation 1. So let us try it out. Starting from the left hand side, you can see we have taken all the terms of the series in the left hand side. What extra we have written? We have written the second last term as well. See, this is the last term, k plus 1th term. So just before it will be the kth term. Fine. So the natural number preceding k plus 1 is k, natural number preceding k plus 2 is k plus 1, and natural number preceding k plus 3 is k plus 2. So just before this k plus 1th term, this kth term will appear. Now when we look at the sum of these k terms, look at equation 1, this is denoting sum of k terms, and what is it equal to? You can easily visualize. So replacing it by the result obtained here in equation 1, we can write sum of all these terms is k times k plus 3 divided by 4 times k plus 1 into k plus 2, and this gets added to the leftover term, which is our k plus 1th term. Now these two need to be simultaneously solved, simplified. How we are going to do that? We will first see what all terms can be taken common out of both. So you will find from the denominator k plus 1 can be taken common as well as k plus 2. And the leftover terms in both, here we are left with k into k plus 3 divided by 4, and this reduces to 1 over k plus 3 only. So taking LCM and solving, you can see this k plus 3 will multiply here and 4 we will multiply here. So it reduces to k into k plus 3 whole square. That will become k square plus 6k plus 9. And 4 into 1 gives us 4, and the denominator is 4 times k plus 1, k plus 2, k plus 3. If we expand the numerator further, it is cube of k plus 6k square plus 9k and plus 4. If you see the numerator is a cubic polynomial now, we will see if we can factorize it further. If you replace k by minus 1, you will find the numerator reduces to 0, which tells us that k plus 1 is one of its factor. You can quickly check. Cube of minus 1 will be minus 1. Then 9 times minus 1 will also be minus 9. So minus 1 and minus 9 becomes minus 10. Over here, replacing k by minus 1, square of it will be plus 1. So this is only 6. 6 plus 4 is also 10. So we are getting minus 10 as well as plus 10. So that gives us an idea that one of the factor is k plus 1. Now when you will divide this expression by k plus 1, you will see the leftover factor is k square plus 5k plus 4, keeping the denominator as it is. And now you see that k plus 1 from the numerator and the denominator can be cancelled out. And we can even factorize this term, which is in the numerator. You can see it is a quadratic polynomial. We can split the middle term. We can write it as k plus 4k, and you will find the two factors it will reduce to is k plus 1, k plus 4. This entire term divided by 4 times k plus 2, k plus 3. Now you compare it with the required right hand side. You will see the required expression is obtained. So what do we see here? We see that the statement is true for k plus 1. We can say pk plus 1 is true, which implies pn is true for all natural numbers, for all n belonging to capital N. Now taking another example, which can be verified through the principle of mathematical induction. Over here you can see we have product of few terms. Let us see what pattern is getting followed in all these terms and then proceed. Okay, see this is 1 plus 3 over 1. The next one is 1 plus 5 over 4. So if you see the numerators of these fractions, they are the odd numbers. Okay, after 3 it is 5, then it is 7 and so on. But if you look at their denominators, they are perfect squares. This is square of 1. First term is having 1 as the denominator here. Second term is having 4 as the denominator, which is square of 2. This is third term, which is square of 3 and so on. The nth term is also mentioned. So we have to prove product of all these will be equal to n plus 1 whole square. So first we have verified the result for n is equal to 1. So when n is 1, the left hand side reduces to 1 plus 3 over 1, that is 4. And the right hand side becomes, you replace n by 1, 1 plus 1 whole square, that is again 4. Now coming to the next condition, when we see it is true for n is equal to 1, now we are ready to assume it is true for n is equal to k. So assuming it is true for n is equal to k, we are going to write the resulting statement. You will find when n is replaced by k, this is what we get. So we are going to use this in order to prove that the result will be true for n is equal to k plus 1 as well. Over here, we have replaced n by k in order to get the statement. So let us see what actually we need to prove. In order to check that, we have replaced n by k plus 1 on the left side as well as on the right hand side. So this is what we have to show now, that product of these k plus 1 terms will be equal to k plus 2 whole square. So we'll begin with the left hand side. So writing the terms in the left hand side, you can see I have written the product of all the terms which we have here. Moreover, we have written the second last term also. If this is the last term now, when n is k plus 1, then just before it will be the kth term, which will be this one. Now, if we use equation 1, then you will find the product of these terms is known to us. What is the product of these terms? It is k plus 1 whole square. Fine. And then this entire thing is getting multiplied with this expression. Simultaneously, we will solve this also. Let us take LCM here. So 1 gets multiplied with k plus 1 whole square, and this is added to 2k plus 3. And this entire expression divided by k plus 1 whole square. So you can easily see we get rid of k plus 1 whole square as it gets cancelled out. Okay, now leftover simplification, we are going to expand this term. It will be k square plus twice of k plus 1 plus 2k plus 3. That is how much? Add the like terms, we get k square. 2k plus 2k will be 4 times k, and 1 plus 3 will be 4. And if you look at this carefully, you will find it is square of k plus 2, which is required on the right hand side. So we could prove that the result is true for k plus 1 also. So we can say pk plus 1 is true, which further implies Pn is true for all the natural numbers. So for all n belonging to capital N. So it is a simple procedure we need to follow in order to verify the result. Now let us change the type of question slightly. You can see the third one is an inequality. Okay, and we will show this inequality can be verified using the principle. So what does the inequality says? It says sum of first n natural numbers. You look at the left hand side, you will find it is denoting sum of first n natural numbers. So we have to show this sum will be strictly less than 2n plus 1 whole square divided by 8. So now proceeding with 1 first. For n is equal to 1, the left hand side will be 1 only. And the right hand side is becoming 9 by 8. So we know very well 1 is smaller than 9 by 8. So we have shown the result is true for n is equal to 1. Now assuming it is true for another natural number k, that means we are assuming sum of 1, 2, 3 till k will be strictly less than 2k plus 1 whole square divided by 8. So this equation we are going to use in order to prove the result for n is equal to k plus 1. So let us first see what we need to prove. For n is equal to k plus 1, we will prove 1 plus 2 plus 3 till k plus 1 is strictly less than, replace n by k plus 1. In place of this k, if it is k plus 1, you will get 2k plus 2 and then plus 1. That makes it 2k plus 3 and whole square divided by 8. So this needs to be proved. Fine. So we will start it from inequality 1. What does the inequality 1 says? It says sum of these k terms is less than 2k plus 1 whole square divided by 8. So we are going to convert it into the required left hand side here. For that what we do? We add k plus 1 on both the sides of the inequality. On the left we are adding k plus 1, on the right we are adding k plus 1. So you can see it is the required left hand side. So now we will only simplify the right hand side. So the left hand side is now sum of k plus 1 terms, which is strictly less than. Here we are going to take LCM and simultaneously we will expand it also. See, this will become 4k square plus 4k plus 1 plus 8k plus 8, multiplying 8 with k plus 1 whole divided by 8. Now that reduces to 1 plus 2 plus 3 till k plus 1 is strictly less than 4k square plus 12k plus 9 divided by 8. We'll factorize the numerator now. This implies 1 plus 2 plus 3 till the k plus 1th term is strictly less than. Now look at this carefully. You will find it is a perfect square and it is square of 2k plus 3 whole square divided by 8. See, this was needed in the right hand side. This is square of 2k. This is 2 into 2k into 3 and this is square of 3. So we can write it as 2k plus 3 whole square. So you could see the result is true for k plus 1. We can write statement is true for n is equal to k plus 1, which further implies the statement Pn is true for all the natural numbers. Now slightly let us change the type of the question and try to verify our principle. The question says, according to the condition, we have to prove 10 to the power 2n minus 1 plus 1 is divisible by 11. So whatever expression is given, we have to show it will be divisible by 11. So we'll check it for 1 first. So replacing n by 1 here, our statement becomes 10 to the power 2 minus 1 and then plus 1 separately. Now 10 to the power 2n minus 2 minus 1 is 10 only. So when 10 gets added to 1, we get 11, which is divisible by 11. So we can show, we have already shown the result is true for 1. Now assuming that the result is true for n is equal to k. So what are we assuming? We are considering that 10 to the power 2k minus 1 and then plus 1 is divisible by 11. This term is divisible by 11. Now if we are saying it is divisible by 11, we can assume it is a multiple of 11. So writing this as 11 times lambda, because we have already mentioned this term is divisible by 11, you can divide it by 11, which is possible only if it is a multiple of 11. So I am considering it as 11 times lambda, where lambda is some natural number. Now we are going to use it to prove the result for n is equal to k plus 1. So now you can see we have done some rearrangement of the terms. If required, we will replace 10 to the power 2k minus 1 by 11 lambda minus 1, shifting 1 to the right side. Now let us see what the statement will be when n is equal to k plus 1. So if I replace n by k plus 1, our statement reduces to this. So we have to show this is divisible by 11. So let us start simplifying this. So we are simplifying the statement for k plus 1. See how we can write the exponent of 10. If you see, the exponent of 10 is 2k plus 2 and then minus 1. So again the terms in the exponent, you can see they are rearranged. We have written it as 10 to the power 2k minus 1 we are taking together and plus 2 separately. Then we also have another term which is getting added to it, that is 1. Fine. Now you can see this exponent 10 base has got exponent as a sum of two terms. So we can write it as product of two separate terms. We can write it as 10 to the power 2k minus 1 into 10 to the power 2. So these are equal steps if you see. Okay, here bases are same. So obviously in the previous step what was happening? The exponents were getting added. So I have converted it into this form so that we can continue with our calculation part. Now you look at equation 1. Equation 1 says 10 to the power 2k minus 1 can be written as 11 lambda minus 1. So this gets replaced by 11 lambda minus 1 and square of 10 is 100, which is getting multiplied to it. Then we will add 1 to the resulting term. Open the entire expression. We get 11 into 100 lambda minus 100 plus 1. Okay, what is minus 100 plus 1? It will be minus 99. So 11 into 100 times lambda minus 99. You will find among these two terms we can take 11 common and we are left with 100 lambda minus 9. Now look at this entire expression. Can we say it is divisible by 11? Obviously, because it is a multiple of 11. So which is divisible by 11. So you can see that we have shown the result is true for k plus 1. When n is replaced by k plus 1, the statement is coming out to be true. Hence we can say the statement is true for all the natural numbers. So Pn is true for all n belonging to the set of natural numbers.